Hello. Let's talk about driving multiparticle or even continuous system, driving the vibration of them. What do I mean by that? Well, this is, if you have a single particle, how you drive it, you apply a force, additional force, driving force in the system. So you can you can drive for this system this one system, and you have another force. You can move this point back and forth. That will also be one way to drive it, uh, and you could apply another force to it, back and forth. So when you drive this system, you notice one of the results that you notice is this has a natural frequency is omega 0. You may remember it's the square root over k over m, k and m. So if I look at this, I have an average power of the driving force. Let's see if you have the average power of driving force versus omega. So say you're driving at f0 cosine omega t. Okay, so that's the driving frequency. And if I look at how the power that's being delivered to the system is this thing. It has a peak at omega 0. So if I drive at different frequency, I get one peak, and there's only one peak here in this system. If I had a system with two masses, for instance, well, I could drive it a couple of different ways. I could just apply additional force on it, additional force on this thing, f0 cosine omega t on A, and leave this guy alone. I continuously all the time apply additional force on this. That's one way to do it. Another way to do it is I can leave this guy fixed on that side, but over here I kind of wave left and right and make sure this so-called zeroth particle, and this is particle A and particle B, is this thing is actually I control its displacement, and this displacement is maybe some A cosine omega t. So the driving force is basically moving this back and forth, and that displacement will have to be included in A, equation motion for A, and then because of coupling it will go into B also. So when we do this, I'm going to have omega and average power. I look at this. You probably know what's going to happen here, right? Because you studied the video before this called coupled system, right? So it's going to be one peak at a normal mode of this system. Okay, even if I'm doing it this way, I will get a normal mode of that system, omega 1, and the normal mode has another normal mode at some omega 2. So there will be two peaks, one at each normal mode frequency. Here I didn't complete it, but you had a one way, and this is the second way for two systems. You had a one way apply force on this, or you could have actually do the displacement here as well. So if you move this guy some a cosine omega t, this displacement here will end up in the equation of motion for this guy, and it will act as a driving force in the equation of motion. So this is the second way of doing the same driving. Now think about how I'm going to drive this guy. I mean, how both ends are fixed. It's kind of like this, both ends are fixed. Well, driving will require you to free up one end so you can apply force on that end or displacement. So let's say I free up this end, but I leave this guy alone. And imagine extending it just a little bit, and then I can attach, here we study vibration this way, right? We study vibration like that. So I can attach a vibrator which is kind of like that. So it's causing a displacement at the 0th particle, but over here the L is this much is L. So I have to extend a little bit so that I can have a node here, right? So if I do this, let's call this some epsilon cosine omega t. So this is the driving frequency. If this driving frequency is just right, like it can actually cause a resonance of that mode. If frequency is low, it's going to, you might practice with take a kind of rope and hold one end and try to practice. You'll see it follows your hand motion, right? But it has a very certain small amplitude of your vibration. But if you vibrate at a frequency that corresponds to this normal mode, you'll see this actually be a very, very high amplitude. Okay, so it's kind of like this. I caught one of the frequencies. So if I were to, it won't surprise you that as I vary this guy's frequency and I look at average power, clearly more displacement, more energy, and so correspondingly you get more energy per unit time, so you get more power. So you have omega 1. You know, in this system you have omega 1, and omega 2 is 2 times that. Omega 3 is, so system is this, right? So those were the normal modes of that system that I'm trying to so-called excite. When you put energies at the normal modes, we use the word I'm exciting normal mode 1, exciting normal mode 2. So here actually, by doing this, I excite this normal mode, and so I'll see a resonance of this, right? And I keep increasing the frequency. I will excite. There's no this wall here. This wall is here, and this is where the node is supposed to be in the original system. So you can see that the vibrator here is going to have to be continuous, right? So this, and it can be very you can get very close to this point, and this can be very tiny amplitude of the vibration. So you have very tiny amplitude of the vibration actually causing this guy to really go up, vibrate way a lot more than this guy is going here. Okay, and so you get another frequency, and then you get another frequency. Well, this is a continuous system, so it will just continue, right? Okay, let's see. If you had this n big system, well, how would you drive this guy? Well, very similar, right? You're gonna drive, maybe take one of these guys out and attach to a vibrator, and we are attaching so close to the where the node's gonna be. Just attach a little bit to the left, okay? And so you're gonna excite very similarly. You're gonna excite omega 1, omega 2, omega 3, but this one kind of end up at omega n, and there are no more normal modes in this system. This one goes on forever, but this one no more normal modes, right? And this is omega 1, and this is 2 times omega 1, this is 3 times omega 1, and so on and so forth. So this is omega 2, this is omega 3. So when you have system like this, you have doesn't mean you can't drive at high frequency. Of course you can drive at high frequency. These are the normal frequency. Just like over here, there were these frequencies you could drive at, but you're not getting resonance, right? You're not getting amplification. When there's a resonance, you get amplification of you're doing a little bit here, but response from the system is far greater displacement, right? So like in a drum, drum has the air here. So that's your system, right? That's the system. That's this thread here. So this is the system. So it's got some normal modes, right? It's got every system, closed system has discrete normal modes. So it's got discrete normal modes. And then when I hit on the drum, what do? If I hit, I excite try to excite or make one of these normal modes, which has some frequency, is got to couple to this system, just like this thing is coupling. So this is driver is the drum, the skin here is a driver to one of the normal modes of this air that's there. And so the air inside there, those particles get displaced larger amount, and so amplifies, so whatever you did here, it amplified by the if the frequency is appropriate, if the frequency is one of the normal frequencies, is going to get amplified. So getting back to this, you can see kind of an application here, but getting back to this, so there are these frequencies which are below the lowest frequency normal mode, and these frequencies are above the highest frequency normal mode. So high frequency is a cutoff, but over here the behavior is very different than between these two guys. So when you try to solve equation, I'm not going to do that in this video. You get solution omega less than omega min, and then omega between omega min to omega max. We'll call it omega max here, cutoff. I like the word cutoff. And then omega cutoff. So I am driving really rapidly. It cannot be coupled with the normal mode, which means it's going to just die out. My effort will be just kind of not have much impact on the vibration, the entire string. Over here, the entire string kind of keeps up with what I'm doing. Imagine you're doing very slowly pulling up and down. So what will happen to this string? The string will just follow your motion, right? So it's not amplifying it, it's just following your motion. So if you were like displacement this little bit, you don't expect the string to do much if you're doing very slowly, right? So it's not amplified. So this region, the names for these regions, you know. So these are reactive regions, and this is a lower reactive region, and this is upper reactive region. And this part is the dispersive part. So this is dispersive region. When you study later on in your electronics class or some place like that, electric circuits, LC circuits, you see these languages get very interesting meaning in the context of the circuits. They also get good meaning in terms of the waves that are propagating. So next up after this will be the propagation of waves. So you can see how I will have a propagating wave. So let's see if this guy was not there. Okay, if this guy was really very continuous, right? For infinity, it just went on forever. Well, and if I wanted to, if I was doing the frequency, so the wavelength. So this is this size. If it was L, it will fit in here, right? So I have a frequency at this thing. That will generate. I will generate this kind of pattern. Had there been a wall, it will just go there and come back. That's what the standing wave, right? So when if there's no wall, it gets generated, but there's nothing to return back. So it's going to go there, and so this pattern will keep repeating forever. And so you can see how having a driver here, some source, this is a source of wave, it can actually generate a propagating wave. So that's the one we're going to talk next. We will start to do progressive waves next in a more systematic way. But it's just a hand wavy way of thinking how progressive waves can be generated at a source. So I'm going to stop here. This is just an intro video to the next topics.